Let's continue. Now we will summarize all info for different frequency bands. We will start with low frequency. Low frequency band was from 30 to 300 kilohertz. These radio waves propagate like ground wave, or ground affects the propagation, mainly ground affects the propagation, not troposphere, not ionosphere. Also ionosphere, but main ground. Here is used vertical polarization because of this effect of a reflection from Earth, and if we have a reflection and polarization is horizontal, two waves, direct and reflected wave, will be with different phase, and in big distance, in long distance, when we sum these two waves, the resultant wave will be zero. So we could use vertical polarization. In these frequencies, antennas are wire antennas, and standard wire antennas are with light of about a quarter of wavelength. Or if their wavelength is from 1,000 to 10,000 kilometers, antenna rate have to be from 250 to 2.5 thousand meters. That is impossible to place such antenna vertically. So there are used some techniques to short these antennas. But antennas have to be vertically oriented, to use vertical polarization. That is very important. And here, close to Sofia, in Vakarel, I think they removed this antenna, but some years ago there was such antenna for they used it for low frequencies, but it was for medium frequencies in original application, but they used it also for low frequencies. But I think they removed it because in Bulgaria now we don't have broadcasting at this frequency. So this waves diffract over obstacles. The wavelength is up to 10 kilometers, so obstacles, mountains are not obstacle for this wave. And there are no problem. And also they travel beyond the horizon, following the contour of the Earth. No problem to propagate to hundreds of kilometers. And also in some cases to 2,000, you could see here, to 2,000 kilometers. Because of low frequency, absorption in the ground is very low. In these frequencies, conductivity of the ground is very high, and it reflects the radio waves without losses. There is no absorption. So ground wave propagates in some cases to 200 kilometers, but at this distance there are also a sky wave, because of ionosphere reflection. They reflect from E, and sometimes where the electronic concentration is low, from F layer, and in daytime they could reflect also from D layer. This ionospheric wave is called also sky wave. Sky wave can be detected in a distance over 300 kilometers. To 400 kilometers, ground wave is main way of propagation. From 300 to 1000, 2000, almost the two type of waves, ground and sky wave, and over 1,000 kilometers we have only sky wave. That is reflected from ionosphere, from Earth sometimes. So applications: radio broadcasting only in the big countries, mainly in the big countries, not only but mainly in the big countries, because they propagate, you see, on very long distances, and it is good for broadcasting in big countries because the quality of broadcasting is not so good. It uses amplitude modulation, and in this case a signal is affected by noise, very high noise, because amplitude could change from attenuation, from multipath propagation, and from everything. Standard time signal, because of stable phase, this is because of a long wavelength and stable phase, it could be used for signal time, standard time signals, also in military and for experimental and amateur applications. It is not more used. There are no many applications because the frequency band is not so wide, and we could transfer very small amount of data. We have from 30 to 300 kHz or 270 kHz frequency band. You could transfer only speech, music with very poor quality, and something like this. It is difficult to transfer data with high speed, only with low speed, and that's all. And also for this application, from space to Earth, it is impossible to use them because they reflect from the ionosphere. Medium frequency. They are propagated by ground waves and reflection from the ionosphere or sky waves, but we desire to use only ground wave because sky waves exist only in the night time. In daytime they are absorbed from the layer in the ionosphere. So in daytime we have only ground wave. In night time we have also sky wave. But I said that you could make this experiment with AM radio. In daytime you will find maybe 1-2 radio broadcasting station in this frequency band from 530 to 1610 kilohertz is this frequency band. But in the night time, it is full with broadcasting station. And in some frequencies, there are more than 2 stations on the same frequency. Ground waves follows the curvature of the Earth, so diffraction is good. The wavelength is from 100 to 1000 meters, but here big mountains are the problem, because the wavelength is up to 1000 meters, and if we have some mountain with height of, for example, 300-400 meters, and our wavelength is in the lower wavelengths, for example around 200 meters, it will be the problem. But they don't have problem with some hills, for example. Radio stations uses also amplitude modulation, like low frequencies, and their coverage radius is around maybe 300-400 meters. It is a little bit different in daytime and nighttime. In daytime, around 300-400 meters. In nighttime, 200-300 meters. Over water, I said this in previous part. Propagation conditions are much better than in the other surface. So maybe distance is up to 10 times bigger, longer than in Earth surface, in our sea level and oceans. So when we have skywave propagation, the distance are around 1000 kilometers, 1500 kilometers between communication points with one hop, and they mainly reflected from E and F, mainly from E and sometimes from F layer when the electronic concentration is lower. D layer absorb medium frequencies in daytime, and therefore we have only ground wave in daytime, and we said that in nighttime we have long wave propagation. Applications: also AM broadcasting, non-directional navigations for maritime and aircraft navigation. In some places there are, I don't know the word in English, far.
Lighthouse.
Lighthouse. Lighthouse, yes. But not light and radio frequency lighthouse. For example, in Shabla there is such. I think most of them is not used nowadays, but some of them are used for navigation in open sea. and oceans, also for amateur radio and for maritime emergency applications. This is only main applications of these frequencies. Also, we could say that it is impossible to use them for radio astronomy because they reflect from ionosphere. Okay. There is very small words for high frequencies, but I will try to explain more. They use mainly skywave because we have limited ground wave path. In these frequencies, ground surface is not so conductive, and Earth surface start to absorb electromagnetic waves. So the path distance is around 20-30 kilometers in most cases. It also is depends on type of surface. If we have more humid Earth surface, the distance will be longer, but for in other cases it will be shorter. If we have overseer propagation, the distance will be like for other frequencies in the previous bands, around 100 of kilometers in this band also, because water has bigger conductivity than dry soil. So we could use for communication mainly skywave. It reflects from F layer mainly in nighttime. In daytime, in some cases for lower frequencies, it is possible to reflect from E layer too, but it is very rare. We could use different frequencies in daytime and in nighttime. In daytime, we have higher electronic concentration and higher absorption in the ionosphere. So we have to use higher frequencies. They could reflect from the ionosphere because electronic concentration is enough, and for these higher frequencies in daytime, I could return in daytime for these frequencies. You could see that this is previous band, this is band we talk about now. So here is the high frequencies of this high frequency band. So for these frequencies in daytime, we have smaller attenuation in the ionosphere than in nighttime. So in daytime, we have to use higher frequencies or frequencies close to the 30 megahertz. I said from 15 to 30 kilohertz, for example. In the night, electronic concentration is lower, so we have to use lower frequencies for reflection. And it is good because in nighttime absorption is lower for whole ionosphere, and there is no problem. So in this frequency band, you could use different frequencies in daytime and nighttime. If you have some a radio device with high frequency band, it is called short waves in the past, and there was some devices like VEF or Selena in these times, and you could see this also in daytime. Is used short waves with wavelength around a little bit higher than 10 meters. In nighttime they used over 70 meters wavelength. If you have such a radio receiver, you could make this experiment too. That is the mainly about propagation of these frequencies and applications. Military and government communication systems, aviation, air-to-ground communications, amateur radio, short wave, international and regional broadcasting. Regional only in distances about 20-30 kilometers around transmitter, and mainly in for international broadcasting in years of communism. Some West radio station like BBC, Voice of America, and something like some other radio station use this band for news in Bulgarian or for news in other languages from East Bloc, and some people listen to them. And this radio station, they at some time they they announce their frequencies for different hours. For example, they said that from 6 to 8 o'clock in the morning they will broadcasting on 50 meters wavelength. Then in daytime they will broadcast, for example, at 15 meters, etc. So maritime, sea-to-shore and ship-to-ship services, over-the-horizontal radar systems, long-distance radar systems, and also citizens band radio service around 27 megahertz. There are so many devices that is used by in the home or some other devices that operates in these frequencies. Some also some remote devices with remote control. At the end of this band, we could use these frequencies for radio astronomy, because in some cases when we transmit or receive perpendicular to the ionosphere, these frequencies don't reflect from the ionosphere. They pass through ionosphere, so we could use them for radio astronomy. And maybe frequencies over 20 Hz is possible to be used for this. If they are not used for other applications, because if you have something in this band, it is impossible to use this for astronomy, because there will be so many devices around maybe that could make big noise in this frequency band. Very high frequencies, mainly line of sight propagation. Here we don't speak about ground wave, because in this case electromagnetic power is a little bit over Earth's surface, not so close to Earth's surface like in previous bands, because Fresnel zones here are smaller. I show you this exercise with Fresnel zones, and the radius of Fresnel zones depends on frequency or on wavelength, and for higher frequency the radius of Fresnel zones are smaller, and therefore ground surface doesn't affect so many these waves like previous one. And we talk about line of sight propagation, not ground wave. A reflection at lower frequencies from the ionosphere. There are some interesting effects, like a reflection from F2 layer for frequencies up to 50 megahertz, sorry, but the angle of accidents have to be very big to make such a radio links. Also a reflection from sporadic E layer. Also we have multipath propagation and tropospheric refraction and tropospheric ducting. I explained this in previous part. Applications, there are so many applications here. Amateur radio, FM radio broadcasting in frequency band from 88 to from 87 to 108 megahertz. TV broadcasting also. Here aviation, communication and navigation, and so many other applications. This is main application. These frequencies could be used for radio astronomy, because for these frequencies the influence of Earth ionosphere is very small. We have reflection only in the lower part of frequency band for frequencies above 65 megahertz. We don't have reflection, and for these frequencies the only problem is the polarization. But for this kind of application like radio astronomy, it is not so big problem. Ultra high frequency. Also line of sight propagation. Here Fresnel zones are more and more smaller than in previous bands. We have multipath propagation. It is very important for mobile communications. And mobile communications are in this frequency band. tropospheric refraction, tropospheric ducting. Here we could produce antennas with high gain and could make radio links of type point-to-point. For previous frequency bands, many of radio links are point-to-multipoint or broadcasting radio links. Here we have to produce point-to-point communication link because of high antenna gain or antennas with high directivity. This is most used frequency band in communications. Now, personal mobile radio, 433 megahertz band, for example. TV broadcasting, mobile cellular networks, 1G was here, 450, around 450 megahertz, around 900 megahertz second G, third G around 2.1 gigahertz, also here. Then 4G, they used for 4G frequencies for mainly for 2G or 900 and 1.8 gigahertz also. Now some of frequencies of 5G are also here. 2.6 gigahertz is in this band. So main of this application. Wi-Fi 2.4, 2.5 gigahertz. Satellite communication L-band with mainly with circular polarization, but for some application it is not problem to use also linear polarization, and some radars also work here for big distances because these frequencies are not affected by the rain attenuation. Also, there is no problem with the ionosphere. We have not big attenuation in the atmosphere here, and this frequency could be used in radio astronomy too. Super high frequencies from 3 to 30 gigahertz. Here we have also line of sight propagation, also have tropospheric refraction. Tropospheric ducting is not usual for these frequencies. Very high directional antennas. Here we could achieve 10,000 of antenna gain. Like this example I give you, 3 meters antenna at 10 gigahertz, around 70,000 times antenna gain. Mainly point-to-point communication with free line of sight, communication distance from 60 kilometers of the lower part to max 5, 7, 8 kilometers of the high frequencies of the band because of rain attenuation. Also, in this band starts molecular attenuation at frequencies around 15, 18 gigahertz. Applications: 5G networks, also Wi-Fi around 5 gigahertz. Main band for satellite communications. Main band for radars and almost all of radio relay links works in this frequency band. A radio relay links is links that use a retranslation of the signal, and they operate on distances from some tens of kilometers to thousands of kilometers. And distance between two radio relay stations is about 40-60 kilometers, and with a retranslation of the radio signal, we could transmit this signal from one point to another point, and distance between these points could reach thousands of kilometers. This band in the lower part could be used in radio astronomy, but for higher frequencies of this band it is difficult because of absorption in the rain. It is possible to receive the signal from the space in this band, but if we have rainy conditions, it will be impossible to receive so weak signals from the space. Only when the sky is clear we could use this band. Extremely high frequency band from 30 to 300 gigahertz. Also a line of sight propagation in this band, in previous band also we could say that there is no refraction, practically no refraction. Rain attenuation and gaseous attenuation are very high in rain for whole band, and gaseous attenuation we have max at 16 gigahertz, around 16 decibel per kilometers. At 22 gigahertz it is not so big, it is 0.1 decibel per kilometer, this is good, no problem, but at 184 gigahertz it is maybe around 20 decibel and more per kilometer, and this is very serious problem for communication because rain affects only when we have a rain, but atmosphere is permanent, and atmosphere affects all the path. Rain doesn't affect all the paths, because if we have heavy rain, it falls on small part of the link distance, but this attenuation affects the whole path, and this is serious problem. Applications: radars for short distances, for example police radars, some of them work in this band. Radio relay links, such like this I said, but not for 1,000 kilometers distance, but only on short distances. Weapon systems, scientific research, medicine, and other non-communication application. And the last band, terahertz, is almost impossible to be used in the Earth atmosphere because of this attenuation. You could see that it is about 1,000 decibel per kilometers, or that means 100 orders of power. Power will decrease with 100 arcs. If we transmit 1 watt, that means that this signal will attenuate 10 on power of 100 times. 10 with 100 zeros to the end. This is imaginary. So it is impossible to use them for communication through Earth atmosphere because of this. Then in infrared band, invisible band, we could use these frequencies for communications. So I think that's all.